Kachowgorithm. I'm Aaron. I'm also joined with Noah and Vade. And yeah, let's talk about this. So the problem we had is that in an array of tweets, we must replace contractions and abbreviations in each tweet with their associated meaning. So for example, lol that is cool turns into laughing out loud that is cool. And we have to go through 1.6 million tweets and compare them to 376 contractions, which is quite a bit of stuff. So we're going to first implement a brute force solution. So we have a list of tweets of length n, and a length of contractions and abbreviations of length m. We go through each tweet looking for abbreviations in each word. Therefore, we go through n tweets m times, giving us a big O notation of O and M. The result of the brute force is that we have an unimaginable amount of time to run, and it takes over 600 seconds, which is incredibly inefficient. Some of the other problems with the brute force algorithm is that going through 1.6 million tweets and comparing every word with every contraction is very inefficient. It also takes a high power usage. We lost 5% of our battery running the brute force algorithm alone. It also takes high computing power usage and an unsustainable sample size as it increases. And so our solution is that we use hash maps to store words. We also create unique keys and improve the overall runtime of the algorithm. And so we have implemented the Kachowgorithm. The name is inspired by the Cars movie, so just like Lightning McQueen, the Kachowgorithm goes very, very fast. We use a rolling hash initialized with a list of contractions of length m to go through the tweet of length n. When a valid contraction or abbreviation is found, the rolling hash will replace it with the correct meaning. There's an average big O notation of O(n) plus m and a worst case of O and m if every single match is a false positive. So let's put the pedal to the metal with the Kachowgorithm. It takes approximately 20 seconds to run 1.6 million tweets. Kachow. So now let's compare the brute force algorithm with our Kachowgorithm and see the differences. So comparing the Kachowgorithm with the brute force, we can see that the Kachowgorithm clearly wins the race here, which in this case we call it the piston cup. And so what about edge cases? Well, there are hashing collisions, and so if a user, for example, types in LOL, it may have the same hash value as LLO, as they carry the same letters. Therefore, we have created the Kachowgorithm license plating fingerprinting technique. By multiplying each letter's ASCII value by 10 to the power of its position, we create a unique value for each word. This value is to be stored in the hash map. And yeah, thank you very much. Ka-chow.
All right. My name is Vade, and now I'll explain to you how the code actually works by showing you the code itself. So let's pop over to the GitHub I've opened here real quick. So to begin with, let me show you how the brute force works. Up here we have some imports, pretty standard. Actually, if you run this, you can remove the first and the last line. That was only used for me to run this in VS Code easily. But you can feel free to remove it to make it run on whatever code editor you want to run it on. So we import some libraries that are essential for us to make this happen. Then we import our data. First we read the contractions file, and then we read the Twitter full file. The Twitter full file is the file containing all the tweets that we want to modify. If you like to upload your own tweets, make sure it's a CSV and change the file path here, and everything else should work the same way. Then we convert the tweets into a string array, and then we create an array of all the definitions, we create an array of all contractions and abbreviations, and once we've done this, by line 22, we have basically all the prep work done and ready to go. So now we can actually start implementing the code. Between lines 24 and 28 are basically some stuff we only use for graphing. We just loop through a bunch of different batch sizes to create a graph to show how long our code takes to run as we change our batch size. But it's not essentially a part of our algorithm itself. So let's begin with the brute force algorithm. we loop through all the batch sizes. That's immaterial in this case. Then we go through every tweet in the tweet subset, and for every contraction, what we essentially do is we create a pattern for the word, accounting for some punctuation before and after. And if the pattern matches, we replace it. Otherwise, we don't. That's essentially how this works. So all this done, as you can see, it goes through two for loops here. That's what makes our O and M and makes this a really, really long running algorithm. So once all this is done, we store all the times for each of the batch size runs. And over here, we graph them in the final few lines. You can ignore these code. This code was just to create another line for reference. So now that you've seen the brute force algorithm, let me show you the Kachowgorithm. The Kachowgorithm has the same thing. We do the same imports here. And now, as you can see in line 17 and 18, we actually create two dictionaries this time. Actually, it's only the one in 17 we used. The one in 18 was for testing purposes later on. We also, again, read in the contractions and the actual tweets. Feel free to replace this with your own tweet CSV, and it should work the same way. Feel free to contact us if you have any questions as to how this runs. So now that we're done that, we once again initialize into string array. We do all the same setup this time, but now this is where our unique license plating comes in. What we do here is we take in a word and we loop through every letter in the word. And as Aaron mentioned to you earlier, we license plate it we multiply the ASCII value of that by 10 to the power of the position of the letter. This gives us an extremely unique key for every single word. So once we multiply for one letter, we do that for every single letter, then we sum up all the values, and that key should be so unique that we severely minimize the number of possible conflicts we have with the key. That way our hash map remains relatively stable. Once we do that, we loop through for every word and create our hash map here. Once we've done that, we have the same startup here. The batch size, this is just for creating the graph once again. So what we do here is for every tweet, we split the word and create like a string array containing every single word. Then we loop through each of those words and we convert it into lowercase, we strip it of any punctuation, and we hash it. We license plate it essentially. Once we get that, we see if that license plate is available in the dictionary. If it is, we replace it. Otherwise, we don't. This is what our unique point is. Because we use a hash map here and we search by key for that word only, we are now bringing down the lookup time from like O of M just to search up the word in the contractions to O of 1 essentially. That's what makes our Kachowgorithm so powerful. Then we just print out the tweets and we graph it over here. That's essentially how this algorithm works. I just want to show you our contractions. Right now we check for about 376 contractions over here. And the accuracy can obviously be improved by adding more contractions to our data set. But the way the algorithm functions will remain the same. So these are the 376 contractions we check for. And actually, our full tweet size, we tested for 1.6 million tweets, and it's so many that GitHub can even handle that. So let me pull up my VS Code here, and this is actually how many tweets we checked for when running this algorithm. We checked for a lot of tweets over here. But that is how our code runs, and feel free to ask us any questions about it. I'll now passing it over to Noah, who will be explaining all the milestones to you.
Now we're going to be taking a deeper dive into the milestones, which kind of represent our progress throughout this project. So into milestone 1, this is where we came up with the brute force algorithm, and it all started just with an idea of how we were going to formulate, how we were going to solve this problem, because it was a big problem, especially with the millions of tweets that we'd have to be going through and the hundreds of contractions, resulting in very large runtimes. So we originally planned it to be ONM runtime, which we did accomplish with the 2D array approach. Our original brute force code here, our pseudocode, ran with a double for loop with a one for loop inside of the other. And then the reason for its slow pace is we checked for each contraction individually. So we looked at each word and then compared it against every contraction to see if it was indeed something that needed to be replaced or if it wasn't. Here's a better visualization of it. For example, LOL, we're looking for that. And if we find it, we will replace it with laughing out loud. So, and then part of the milestone as well that we found, part of the success of it was that we were able to find a lot of unexpected cases here. So for example, here, our example says bololers. So if before our algorithm, when we first created it, it would replace this lol with the laughing out louders, which like obviously isn't the intended use of our algorithm. So we developed it to look for spaces and punctuation on every side, as Veda explained in the code. So yeah, it made it really easy to find these unexpected cases when we were going at it milestone by milestone. The second milestone was where we started to come up with our Kachowgorithm. After we came up with a solution for the brute force, then it was time to think a little bit deeper and optimize the solution. So here it's just one for loop that uses a rolling hash with a hash map, allowing us to, on average case, get ON plus M runtime. An example here shows that we're looking for the similar to the last visualization, it looks for the word, but then it searches the unique license plate ID that we create in our hash map, resulting in that O1 comparison rather than the OM comparison that we had on the previous algorithm. So an edge case that Aaron explained in the slides here is that we could hash the same, resulting in hash collisions if the words or the letters were just out of order, which is why we came up with the license plate ID system to prevent that, which resulted in us not running into collisions during our algorithm's runtime. So when we get into 3 and 4, this is where we actually implemented our algorithm. The important points of these ones is we can actually see we came up with the graphs, it worked, it ran in ONM time for our brute force, which is what we're expecting. And then for milestone 4, it ran in ON plus M time as expected, very fast, actually under 20 seconds was actually very shocking to us, especially considering the other one went over 600 seconds. Throughout the project, we divided up tasks really well. For the code, we kind of just mobbed it, working on it all together, and then we worked on everything just as a group at the same time to make sure everyone was putting in the exact same amount of time, the exact same amount of effort. So it worked really well in the end, and we all got to learn a little bit more about coding and a little bit more about problem formulation and optimization of algorithm problems. So that was really cool. And then really the summary is like our algorithms ran in the runtime that we were expecting them to. The comparison obviously shows that our faster running Kachowgorithm ran much faster than the brute force, which is as we expected, but it's nice to see that that worked out. We have our GitHub and dataset links if you want to check those out. Our dataset, we used one for the tweets, and then we used 2 for the contractions and acronyms, and then we just combined it into one for the replacement. And then all our code is on the GitHub. And then we cited anything we used for inspiration during the research phase. We'd like to thank you for listening to this video. This project was a very educational and very good learning experience just for how to formulate, go at like a bigger size problem and come up with not only a brute force solution, but an optimized solution. And we thank you for your